Listen, I need to tell you something that's going to shake everything you thought you knew. Einstein, the greatest mind in physics, spent the last 30 years of his life fighting quantum mechanics with every ounce of his being. God does not play dice with the universe, he famously declared, his voice trembling with conviction. And what happened next? Every textbook, every physicist, every documentary on Earth tells you the exact same story. Einstein lost. Bohr won. Quantum mechanics triumphed. The old man died stubborn, isolated, and completely wrong. But here's what's going to disturb you. What if I told you that's not what actually happened? What if Einstein was right all along and we've wasted an entire century, 100 years of human genius, pursuing the wrong interpretation of quantum reality? My name is Roger Penrose. I won the Nobel Prize for proving that black holes are inevitable consequences of general relativity. I've spent 60 years of my life working on the deepest, most fundamental problems in physics, and I'm here to tell you something revolutionary. Einstein's intuition about quantum mechanics was absolutely correct. Not his conclusions, mind you, but his intuition. And the difference between those two things, that subtle but crucial distinction, has cost us 100 years of progress. Let me take you back to 1927, to the Solvay Conference in Brussels. Picture this scene. The greatest minds in physics gathered in one room, the air thick with tension. On one side, Niels Bohr and the quantum revolutionaries, young, confident, ready to overthrow everything. On the other side, Albert Einstein, increasingly isolated, increasingly desperate to prove them wrong, fighting a battle he seemed destined to lose. The Copenhagen interpretation had just been formulated, and it said something deeply, profoundly strange. Quantum particles don't have definite properties until you measure them. Think about that. The act of observation, conscious measurement, collapses the wave function and creates reality itself. Before measurement, particles exist in superposition, simultaneously in multiple states. Schrödinger's cat, both alive and dead at the same time. Einstein hated this idea. He absolutely hated it with a passion that consumed him, not because he was conservative or stuck in his ways. Remember, this was the man who destroyed absolute time and space, who revolutionized our entire understanding of the universe. He hated it because it violated everything he knew, everything he felt in his bones about how reality should work. Do you really think the moon isn't there when you're not looking at it? He asked, his frustration palpable. But here's what everyone, and I mean everyone, gets wrong about Einstein's objection. They think he couldn't accept randomness. God does not play dice. Therefore, Einstein must have been a determinist who wanted clockwork predictability, a universe running like a perfect machine. That's not it. That's not it at all. Einstein's real objection was much, much deeper, more profound than anyone realized. He thought quantum mechanics was incomplete, not wrong, but incomplete. Like a beautiful equation with a variable left undefined, a masterpiece with a missing piece. In 1935, he published his masterpiece of criticism, the EPR paper, co-written with Podolsky and Rosen. It described what we now call quantum entanglement, one of the strangest phenomena in all of physics. Two particles, entangled at creation, separated by vast distances across the universe. Measure one, and you instantly know the state of the other, faster than light itself. Spooky action at a distance, Einstein called it, his words dripping with sarcasm and disbelief. His argument was elegant, devastating, and seemingly irrefutable. Either quantum mechanics is incomplete, there are hidden variables we haven't discovered yet, or locality is violated. Information travels faster than light. Nature has instantaneous connections across the entire universe. Einstein thought this was a reductio ad absurdum, an obvious logical impossibility. Surely locality must be preserved. Surely nothing travels faster than light. That's the foundation of relativity. Therefore, quantum mechanics must be incomplete. Then in 1964, something extraordinary happened. A physicist named John Bell did something that changed everything. He turned Einstein's philosophical argument into an experimental test, something that could actually be measured in a laboratory. Bell's theorem proved that no local hidden variable theory can reproduce quantum mechanical predictions. You can have locality or you can have quantum mechanics, but you cannot have both. The experiments came, one after another. Aspect in 1982, Zeilinger in the 1990s, over and over again, each one confirming the impossible. Quantum mechanics won. Entanglement is real. Non-locality is real. The universe really does have instantaneous correlations across arbitrary distances. So Einstein was wrong, right? Yes, he lost. Bohr won, case closed, end of story. No, not even close. Because Einstein was wrong about locality, I'll admit that, but he was absolutely, fundamentally right about incompleteness. Listen carefully to what I'm about to tell you. The Copenhagen interpretation says the wave function collapses when a conscious observer makes a measurement. But what counts as an observer? Does it need to be human? Does a cat count? A bacterium? An electron detector? Where exactly is the boundary between quantum and classical? No one knows. The theory doesn't tell you. It's incomplete. And there's something even worse, something that should have bothered everyone from the beginning. The Schrödinger equation, the fundamental equation of quantum mechanics, is completely deterministic. It evolves smoothly, predictably, in a purely mathematical way. No randomness at all. But then measurement happens, and suddenly, discontinuously, the wave function collapses. The system jumps from superposition to a definite state. This collapse is random, unpredictable, and completely unexplained by the Schrödinger equation. So quantum mechanics has two rules that contradict each other. Rule 1. When you're not looking, systems evolve deterministically according to the Schrödinger equation. Rule 2. When you look, the system randomly collapses. This is insane. When does Rule 1 stop and Rule 2 begin? What is looking? What is measurement? The theory doesn't say. Einstein saw this clearly. He saw the gap, the missing piece, the place where quantum mechanics waves its hands and says, and then a measurement happens, without explaining what a measurement is. For 80 years, physicists have papered over this gap with philosophy instead of physics. The many worlds interpretation says there is no collapse. The universe splits into parallel branches every time a quantum event occurs. I find this view philosophically cowardly and mathematically lazy. It explains nothing by multiplying entities beyond necessity. The orthodox view, shut up and calculate, says, don't ask what's really happening, just use the equations and get results. This is pragmatism masquerading as science, intellectual surrender dressed up as wisdom. But there's another possibility, one that Einstein would have loved if he'd lived long enough to see it developed. What if wave function collapse is a real physical process? Not observer-dependent, not subjective, but objective, triggered by physical conditions in the universe itself. This is the view I've spent 40 years developing, pouring my life into. I call it objective reduction, or OR for short. The idea is this, and it's beautiful in its simplicity. Quantum superpositions are unstable. They can't persist indefinitely. When the quantum state represents significantly different configurations of space-time geometry, when the superposition involves different gravitational fields, space-time cannot sustain both possibilities simultaneously. The space-time geometry becomes ill-defined, inconsistent with itself. And after a certain threshold of gravitational self-energy difference, the superposition must collapse objectively, physically. No observer required. The moon is there when you're not looking at it because the moon's mass creates such an enormous gravitational self-energy that quantum superposition cannot be sustained for even a femtosecond. Collapse happens immediately, objectively, due to gravity. But for tiny systems, electrons, photons, individual atoms, the gravitational self-energy is minuscule. Superposition can persist for seconds, minutes, even hours in carefully isolated experiments. No collapse occurs until the gravitational threshold is reached. This solves the measurement problem completely. There is no mysterious boundary between quantum and classical. There's only a threshold, a physical, calculable threshold beyond which superposition becomes gravitationally untenable. And here's the beautiful part that brings tears to my eyes. Einstein's greatest insight was that gravity is geometry, mass and energy curve space-time itself. What I'm proposing is that quantum superposition represents uncertainty in space-time geometry itself, and the universe, being a consistent geometric structure, cannot tolerate indefinite uncertainty in its own shape. Collapse happens when geometry demands it. This is what Einstein was searching for in those lonely final decades. Not hidden variables, not determinism, but a physical explanation for wave function collapse, something built into the fabric of space-time itself, not dependent on consciousness or measurement or philosophy. If we'd taken Einstein's incompleteness objections seriously, if we'd searched for objective physical collapse mechanisms instead of inventing metaphysical interpretations, we might have unified quantum mechanics and general relativity 50 years ago. Instead, we spent a century arguing about whether the moon exists when we're not looking, wasting the brilliance of generations. Now I must be honest with you, completely transparent. Objective reduction is not yet proven. The experiments required to test it are at the absolute edge of current technology. We need to create quantum superpositions of massive enough objects to trigger gravitational collapse in measurable time frames. We're getting close, tantalizingly close. Experiments with large molecules with optomechanical systems are beginning to probe the regime where OR predicts deviations from standard quantum mechanics. But even if I'm wrong about the specific mechanism, even if gravity isn't the source of objective collapse, Einstein's point stands unshaken. Quantum mechanics as currently formulated is incomplete. Something is missing. Some physical process, some law of nature must explain why macroscopic objects don't remain in superposition forever. The Copenhagen interpretation doesn't answer this. Many worlds doesn't answer this. Only a theory with objective physical collapse can answer this fundamental question. And that's what Einstein was really arguing for all along. Not dice or no dice, not determinism or randomness, but completeness. A physics that explains why things happen, not just how to calculate probabilities. Do you see the tragedy now? The heartbreaking waste? Einstein died in 1955, thinking he'd lost, thinking his life's final work was meaningless. The quantum establishment moved on without him, leaving him behind like yesterday's news. His last decades were spent in isolation, searching for a unified field theory that everyone else thought was a fool's errand. But he was asking the right question, the most important question. How do we unify quantum mechanics, a theory of the very small, with general relativity, a theory of gravity and geometry? The answer, I believe with everything in me, lies in recognizing that quantum collapse is a gravitational phenomenon. Superposition isn't just a matter of information or probability, it's a matter of geometry itself. And when geometry becomes inconsistent, nature must choose. That choice, that objective collapse, is what we experience as the definiteness of reality. If I'm right, then Einstein's geometrical instinct, the insight that gave us curved space-time, black holes, gravitational waves, extends all the way down into the quantum realm. Gravity isn't just a large-scale force governing planets and stars. It's the mechanism that makes the quantum world classical. It's the reason you can't be in two places at once. And consciousness, that's where it gets truly interesting. where physics meets the deepest mystery of existence. If objective collapse is real, if it happens in the brain's microtubules as I've proposed in the OR theory, then consciousness isn't observing collapse. Consciousness is experiencing collapse. The moment of quantum choice becomes the moment of subjective experience. But that's a story for another time, a whole other journey. What I want you to understand today, what I need you to grasp, is this fundamental truth. Einstein wasn't wrong about quantum mechanics. He was wrong about locality, I'll grant that. He couldn't accept non-locality, and the experiments proved him wrong on that specific point. But on the deeper question, the question that really matters, is quantum mechanics complete? Einstein was absolutely correct. It's not complete. Something is missing. And finding that missing piece is the key to quantum gravity, to understanding consciousness, to completing the physics that Einstein and Bohr both sought, but neither fully achieved. We've wasted 100 years because we declared victory too soon, because we were arrogant. We sided with Bohr, canonized the Copenhagen interpretation, and stopped asking Einstein's question. It's time to start asking again, with the humility to admit we might have been wrong. So the next time someone tells you Einstein lost the quantum debate, you can tell them he lost the battle, but the war isn't over, not by a long shot. Because quantum mechanics as it stands today is exactly what Einstein said it was. Incomplete, brilliant, predictive, extraordinarily useful, but incomplete. And somewhere in the missing piece, in the objective physical mechanism that collapses wave functions and makes reality definite, lies the answer to the deepest question in all of physics. How does the quantum world become the classical world we experience every single day? Einstein spent 30 years searching for that answer, 30 years of his genius dedicated to this quest. He died without finding it. But he was looking in the right place. In geometry, in gravity, in the fundamental structure of space-time itself. And if we're brave enough to follow where his intuition pointed, we might finally finish what he started. Not God playing dice, and not God sitting idle either, but God as a geometer, building a universe where quantum uncertainty must eventually yield to gravitational necessity, where superposition collapses not because we look, but because space-time itself demands coherence, demands consistency. That would be a physics worthy of Einstein's vision, complete, geometrical, true. And it would mean that the old man, isolated in Princeton, scribbling equations that everyone else had abandoned, working alone while the world moved on, he wasn't wrong after all. He was just a century ahead of his time.